So we are talking about chapter 18, equivalence relations. So we have defined a set, and then we have defined a relation on that as a subset of the Cartesian product of a set. We have given some examples of the relations, and then we have given a definition of an equivalence relation. And a relation is an equivalence relation if it is reflexive, symmetric, and transitive. And then we have examined all of these examples of relations, that which of them could be equivalence relation. Okay, perfect. Now we will talk about the equivalence classes. Perfect. So let's say we have a set, and we have an equivalence relation. Okay, on the set S. Now for an element A inside the set S, we define that CL class of A is a subset S which contains the element S inside, such that S is an element of S and S is related to A. So the class of A contains all those elements from the set S which are related by this equivalence relation to A. Okay, so we say that thus class of A is the set of things that are related to A. The subset the CL of A is called an equivalence clause of this equivalence relation. The equivalence classes of an equivalence relation are the subsets CL of A is A ranges over the elements of set S. Okay, let's define an example. Name it 18.2. We say that let M be a positive integer and let this be the equivalence relation on the integers is A is related to B if and only if A is congruent to B mod M. Okay, what are the equivalence classes of this relation? What are the equivalence classes of this relation? So let's answer this. We say that CL of 0 is going to be the elements inside the integers such that S is congruent to 0 mod M. Okay. CL of 1 is going to be the elements from the integers such that S is congruent to 1 mod M. And similarly, CL of M minus 1 is equals to S from the integers such that S is congruent to M minus 1 mod M. Now we claim that these are all the equivalence classes. Okay. So we claim that these are all the equivalence classes. So we can prove this claim is that for if n is any integer, then by proposition 10.1, this would be in the lecture videos for the chapter 10. There are integers q comma r such that n can be written as qm plus r. This is nothing but Euclidean algorithm we are talking about, with 0 less than r, r less than m. Then n is congruent to r mod m. So n belongs to the equivalence class of R, which is one of the following listed above. Moreover, the equivalence class of n is going to be a set inside a set which contains s inside this integer such that s is congruent to n mod m. And if you look at this, this is nothing but s inside z such that s is congruent to r mod m, and this is similar to the equivalence class of R. Hence, any equivalence class CL of n is equal to one of those listed above. Now, we conclude that that there are exactly m different equivalence classes, CL of 0, CL of 1, so on up to CL of m minus 1. And note that every integer lies in exactly one of these classes. Perfect. Now let's talk about another example. (18.3). Now consider the equivalence relation that S is a set which is all people in built-in and A is related to B if and only if A and B have the same father, the universal relation. What are the equivalence classes? What are the equivalence classes? Okay, let's answer this. What we can say, so let's take that if A is an element inside S, so let's take a British person, then the equivalence class for that British person is the set of all people with the same father is A. So in other words, if F is the father of A, then the equivalence class for A consists of all the children of F. So one way of listing all the equivalence classes is as follows. Let F1 to Fm, say Fn, be a list of all fathers of people in Britain. So if Ci is the set of children of Fi living in Britain, then the equivalence classes are C1 to Cn. Perfect. We now prove a general property of equivalence classes. Recall from chapter 16 that a partition of a set S is a collection of subsets such that each element of S lies in exactly one of these subsets. So another way of putting this is that the subsets have the property that their union is S, and any two of them are disjoint. So we prove this by we give this by proposition. So let's say proposition 18.1, let S be a set and let an equivalence relation on this set then the equivalence classes of this equivalence relation form a partition of the set S. Okay, so for a set, a partition contains subsets of that set, and then if you take the union of all those subsets, that will be the set S itself. Okay, so by following that concept, we have to prove that the equivalence classes are the subsets of the set S, and then those equivalence classes, if you take the union of them, you will get the set S again. Okay, so let's prove it. If A is an element inside S, then since A is related to A lies in the equivalence class, CL of A, right? We need to show that A lies in only one equivalence class. So suppose that A lies in CL of S and CL of T. In other words, A is related to S and A is related to T. We show that this implies that CL of S is CL of T. Okay. Now let X belongs to the equivalence class of S, then X is related to S. Also, S is related to A, and A is related to T. So, by transitivity, X is related to T. Hence, X belongs to the equivalence class of S, then X belongs to the equivalence class of T. Now, similarly, if X belongs to the equivalence class of T, then X is related to T, and also T is related to A, and A is related to S. So X is related to S, showing X belongs to the equivalence class of T, then X belongs to the equivalence class of S. We conclude that the equivalence class of T, or you can say S, is equivalence class of T is required. So we are saying every element inside the equivalence class of S is equals to every element inside the equivalence class of T. Thus, any element A inside the set S lies in exactly one equivalence class. Okay. Here we will end this part of the lecture. Thanks so much. Bye.